Hello, everyone. Thank you for joining to this tutorial. And in this tutorial, we actually will have three parts. The first part is we are going to talk about scalable GNN trainings, and we will talk about like algorithms and systems for scalable GNN training. And then we'll talk about GNN research and development at Amazon. And then the last part, we will talk about how we deploy GNNs for real-time applications in the cloud, basically in our cloud service. First, I will present the first part, and I'll talk about large-scale GNN training. And my name is Zheng. I'm a senior applied scientist in AWS AI. So in this talk, I will talk about the techniques we have developed for training graph neural network on large graphs. So I'll start with some general introduction. So basically, in the industry, many of the problems we have encountered can be represented as a graph. And for example, here we give two examples. So if we want to do fraud detection, we can use you can use all the users and devices and credit cards and locations and to form a graph. And in this case, we want to detect the fraudulent users. And in the context, if we formulate this problem as a graph machine learning problem, then this is actually a node classification problem. And for movie recommendation, then we can connect users and movies to form a bipartite graph, and then we want to predict which movies a user likes. So in this case, then this is a typical link prediction problem in the context of graph learning. Many of the industry applications can be seen as a node classification or link prediction problem, and usually those we need to perform these two tasks on very large graphs, like with a graph with like hundreds of millions of nodes or even billions of nodes. And then graph machine learning is just one type of graph. So graph neural network is just one type of graph machine learning algorithm. It is basically a family of neural networks to learn the node and edge and graph representation to make a prediction. So the main difference between a graph neural network and the previous graph machine learning method is that a graph neural network looks at the node ego network to compute the node representation, and the ego network here means that the subgraph formed by all the nodes that are up to like k hops away from the target node. And in this example, the k actually is equal to 2. So now, given this ego network, the GNN wants to use a function to compute the representation of the target node by using the information in that ego network. The information here includes both the graph structure of the ego network as well as the node and edge features in the ego network. And the function is usually called encoder. It is learnable and is usually trained in an end-to-end fashion. So the GNN research started probably like 7 to 8 years ago, and recently it becomes really popular. And GNN actually is popular, also very popular in the industry as well. So the main reason that GNN becomes popular is that it achieves a state-of-the-art performance for solving many problems in a large number of domains. We can take a closer look at what is GNN. So one way to formulate the GNN is the message passing model. The idea of message passing is that nodes will send messages to their neighbors, and then each node will aggregate the messages from their neighbors, and then use those aggregated results to update its representation. So the figure on the left is just a simple example to illustrate the idea. So for example, the node V2, V3, V4, and V5 send messages to V1, and then V1 get all the messages and then use the messages to update its representation. And the figure on the right shows a mathematical formulation. It runs a message function on each edge to compute a message, and then the destination node will aggregate all the messages and use those aggregated results to update its own node representation. And this formulation shows how message passing works in a one GN layer, and then if we can stack multiple GN layers to capture the information from nodes that are multiple hops away. So here is one example of a graph neural network. So more concrete example of graph neural network. This is, in this example, it is we show a graph convolution network, and this is probably the one of the simplest and yet quite effective GN model. In the GCN model, then each layer of the GN updates the representation of a node by first averaging the representation of its neighbors, including itself, and multiply it by a layer-specific learnable weight matrix, and then apply a nonlinear function to generate the embedding. And again, so in the first layer, the representation that are used as an input depends on the node feature. So this is so basically the first layer will take the node features as input. So this is how GN is able to compute the representation that can capture both the information from the features and also from the topology of the graph. So here, this is a very brief introduction of graph neural network. Now let's take a look how scalable GN training works. And in this talk, we'll start with the training algorithm. So one way to train a GN model on is actually full graph training. With this method, we basically will have every node to send messages to its neighbors, and then every node will receive messages from their neighbors and then update its own representation. So if we do message passing in this way multiple times, as shown in this figure, then a node will receive the messages from multiple hops away. And then this training method usually actually only works for a small graph because the memory consumption of this method actually grows linear with the number of nodes in a graph. So if a graph is very large, right, like millions or even even larger, then it's very hard to keep all the data in a single GPU memory to train the model. So a more scalable training method is mini-batch training. So the way of sampling mini-batch, one way of sampling mini-batch on a graph is to first randomly select a small number of target nodes to form a mini-batch. And then for each target node, we will extract its ego network and structure the required computation in a form of a tree. And so this is basically the computation graph associated with the target node. So the figure on the right basically shows an example of such a computation graph. So in this example, basically, where if in order to compute the final representation of node 1, using a two-layer GN, we need first to aggregate the messages from its neighbors that were computed with the representation from the first layer, right? So then, in order to compute the representation, the representation of the neighbor nodes 2 and 4 then we need to aggregate the messages from its neighbors involved in the and then we need to aggregate messages from their neighbors. So basically, we need to access read the node features of node 1, 7, and 8. right? So this is basically how we need to form a how we form a computation graph for a mini batch. We actually evaluate these two methods, and to really run the full graph training on a large graph, in this experiment, we run the entire experiment on CPU. And the figure on the right shows the time used for the model to train until it converges. We can see that a mini batch training is usually many times faster than full graph training. The difference is more significant on a larger graph. So, for example, OGB and papers 100M, mini batch training is about like 100 times faster than the full graph training. And we believe that the difference will become even larger when the graph is even larger, like a graph with like billions of nodes. Therefore, we usually use mini batch training to train the graph neural network in the industry. So given the advantage of mini batch training, so from here we will only talk about mini batch training in the remaining of the tutorial. Even for mini batch training, we still can have 3 different ways to perform to train. So basically, we can perform mini batch training on a single GPU. We can perform mini batch training on multiple GPUs, and then we can perform mini batch training on multiple machines. So this tutorial will briefly go through each of them. So for mini batch training on a large graph, we usually need to keep the entire graph data in the CPU memory because we cannot really keep the graph data in the GPU memory. Then we need to sample a mini batch from the graph in the CPU memory. Then we move the mini batch to the GPU for the forward and backward computation to estimate the gradient of model parameters and update model. Because we have to perform the mini batch sampling on this, so basically this is how this figure illustrates the single GPU mini batch training. And because we have to perform the mini batch sampling on CPU and copy data to GPU for every mini batch. Mini batch sampling and data copy to GPU are usually the bottleneck of the system. So one way to accelerate the mini batch computation is to perform asynchronous mini batch sampling on CPU. So by using this optimization, when the GPU is performing the forward and backward computation to estimate the gradient of the model parameters in mini batch 0, and the CPU is already performing the mini batch sampling and data copy for the next mini batch, so basically the mini batch 1. And then when the GPU finishes the batch, the computation on batch 0, then we can move the batch 1 to GPU and perform the mini batch computation. And then the CPU will move on to work on the batch 2 and so on. So in this way, we can halve the computation time on CPU or the GPU and speed up training. And also this optimization actually does not change the training algorithm. So it will not affect the model performance. And in other words, we basically get the acceleration for free, almost for free. Then we can extend this single GPU mini batch training to multi-GPU mini batch training. So we can use multiple GPU to further speed up the entire training process. So in the multi-GPU training, we need to create a process for each GPU. So then each process will sample mini batches in the CPU independently, and then they will move the mini batch to GPU for mini batch computation. inside a process, inside a process, the computation is the procedure we do for mini batch sampling and mini batch computation is the same as a single GPU mini batch training. Then the multiple processes will synchronize with each other to update model parameters. In this case, the main thing is, in this case, the graph data are still stored in the CPU memory, but they are shared among the processes so that we actually, in a single machine, we only need to keep one copy of the graph data in the CPU memory to reduce the memory consumption. Then, after we have the multi-GPU mini batch training, we may want to extend to multi-machine multi-GPU training. Although the extension may not be as simple as before. So when we, the whole reason that we want to have multi-machine multi-GPU training is that usually the main reason is that the graph data is too large to be stored in a single machine. So we want to extend to multi-machine multi-GPU training, and we can, so that we can work on a larger data set. So to do that, we need to partition a graph and have each machine to work on a single, on graph partitions. And to enable scalable multi-machine multi-GPU training, we designed this DGL to do that. So with this DGL, we need to first to partition a graph and then store the graph partition in a cluster of machines. And then this DGL provides two components to enable this multi-GPU distributed training. So it provides a sampling component that samples the mini batch from a distributed graph in a cluster, and it also provides a storage component that stores the node features and edge features in a cluster of machines, and fetch those features to construct mini batch. And once we can construct a mini batch, the remaining part for multi-machine distributed training will be the same as multi-GPU mini batch training. So basically, each trainers will get a mini batch and then perform the forward and backward computation as usual, and then it will use the PyTorch distributed to synchronize and then update the model parameters. So graph partitioning, as I mentioned earlier, is a very important step for this DGL. So, and this DGL adopts the MITIS to partition a graph, because MITIS is a very efficient graph partition algorithm and also can split a graph into very good partitions. To have a very more efficient distributed mini batch sampling, we actually duplicate some nodes in graph partitions. And in this way, we can ensure that the mini batch sampled from a cluster of machines are exactly the same as sampled from a single machine. And this will ensure the good model performance from distributed GNN training. And we also, when we partition a graph, we also add some balancing criteria so that every partition can have roughly the same number of nodes and edges. This will help us to achieve a load balancing during the distributed training. So basically, all the trainers will run at roughly the same speed. Then another thing is that in the industry, actually, majority of the graph is heterogeneous. So when we design this DGL, we also want to support, like you want to make sure that our graph partitioning supports heterogeneous graph, and we also we also optimize the graph partitioning for heterogeneous graph. So the way we partition a heterogeneous graph is we actually first convert a heterogeneous graph in a homogeneous graph format, and then we will partition this homogenized graph. And then, but then we add some balancing criteria to ensure that every graph partition will have roughly the same number of nodes and edges for each type. So in this way, again, as before, that we want to make sure that the distributed training will not have the load balancing issue. So after we partition a graph, then every machine will store a graph partition in its own CPU memory. This is very similar to multi-GPU training as we see. As we see before. So this DGL will run a mini. The main difference is that this DGL will run a sampling server and a KV store server on each machine to support distributed sampling and distributed data and node and edge feature storage. To sample a mini batch, this DGL will go to its local sampling server and also the remote sampling servers to sample a complete mini batch. And this sampling process happens in CPU. After getting a mini batch, this DGL goes to the KV store to read the node features and edge features to construct a complete mini batch. And then we will copy the entire mini batch to GPU. To accelerate the mini batch sampling, we can use the very similar strategy as we used before to overlap the GPU computation, the mini batch sampling in the CPU and the mini batch computation in GPU. By using this design, we can perform a distributed GNN training on a graph with 100 million nodes in a cluster of 4 machines. And this DGL supports both CPU and GPU training. However, the GPU training is usually multiple times faster than CPU training for GN. After we have having this DGL for distributed GN training, and we hand it over to customers, and we noticed that it is one pain point is that it's very difficult to partition to load a really large graph to this DGL. And usually users' data, graph data, are stored in a tabular format. So it's really a non-trivial effort to convert a tabular data to the graph format that can be used by this DGL. And when the graph is very, very large, think about a graph has like billions of nodes and tens of billions of, or even hundreds of billions of edges. So to simplify the data loading process for the really large graph, this DGL provides a distributed graph partition pipeline to convert users' tabular data to graph for distributed training. And to use this pipeline, a user needed to store the edges of a graph in a list of CSV files, and then store the node features and edge features on NumPy files. And once users provide their graph data in this format, then the pipeline will load the data and partition the graph and convert data to the format that can be used by this DGL for distributed training. We verify this DGL and this distributed graph partition pipeline on a graph with 4 billion nodes and 30 billion edges. And we perform this experiment in a cluster of 10 G file instances. So for people who are not very familiar with the AWS instance types, G file instance basically has 8. This G file instance basically has 8 GPU, 8 GPUs, and each machine has about 700 gigabytes of CPU RAM. And we run another classification task for this data set, and then this graph has about 140 million nodes in the training set, and this entire training takes about 20 minutes per epoch, and then the load the entire graph into this DGL takes about 3 hours. So even though it looks like the distributed data loading is still very expensive, but I mean, the graph loading process actually only need to perform once, and then we can use it for many distributed trainings, and so its overhead can be amortized. But overall, we can see that this DGL supports distributed training on very large graphs, and a training those Zheng have performed distributed Zheng training on very large graph is actually quite feasible, and it's not as expensive, as many people think. So the question is whether or not after we do this asynchronous mini batch sampling, will the mini batch sampling on CPU still be the bottleneck? I mean, it may still be the bottleneck. The idea here is that we want to overlap the CPU computation and GPU computation, so that at least we can, let's say, if the CPU sampling actually takes more time than the GPU computation, then the GPU computation becomes free, and right. So we will never observe any. We will never observe any time is required used for the GPU computation. But of course, we definitely, if the CPU sampling is definitely a bottleneck, then we definitely need to accelerate the CPU sampling. And there are many techniques we can do. And I just show you a very simple example of how to optimize this mini batch training in this context. Cool. Let's move on to the next part of the tutorial.
Yeah, thank you, Daf, for the great first part of the tutorial about how we scale essentially training in like billion node graphs and hundreds of billion edges. So in this second part of the talk, we will mainly focus essentially on how we perform like research and development of GNNs within Amazon. So as Da mentioned, the main tool we use to implement everything we do here is the Deep Graph Library, or DGL for short. And one of the main essentially advances in DGL is the introduction of the distributed DGL that was mainly developed by Da, and really helps you to scale to billion node graphs, which is really the bottleneck when we are talking about industry level applications. So our mission in the AWS GraphML team is to first simplify the research and development of graph machine learning, such that everyone really can contribute to this field and help the field grow. We do that a lot by the open source tool that's called DGL, right? And we also try to maximize the impact of graph machine learning across Amazon by providing scalable frameworks that run like company-wide and scale to billions of nodes graphs. And also we maximize the impact of graph machine learning across the businesses by providing these graph neural network services in the cloud, which Soji will give you a lot of detail about, and he has been the main owner of NeptuneML, right? So this is like our high-level mission, right? But to satisfy this mission, we are called to do research in two different areas. So the first research area is scalable training. So how do we scale the training and inference to graphs that exist in Amazon and in other businesses that scale to like billions of nodes and trillions of edges? So to do so, we use heavily this DGL tool, but we also use a lot of other innovations. But besides this, we also want our models to realize impact, realize benefit in like actual performance, right? So to do that, we are researching a lot of different model performance directions, from unsupervised learning to distillation. And we also study different applications of GNNs in essentially a healthcare domain, or for example, in recommendation systems. So today, I will briefly talk about the following topics. So I will talk a little bit about the TGL, which is the temporal graph library that we developed in AWS. Actually, one of our brilliant interns mainly developed TGL, and it really helps you scale also temporal graph learning. And also we will talk about two other works that has been used in our group about active learning and language models and GNNs. So temporal graph library, or TGL otherwise. So what are the reasons that we started exploring this direction? So most of the existing temporal GNN models have different data sets, often unique, and they lack comparison with others. Also, the codes are evaluated on small data sets, and usually they use a single GPU kind of training framework. And the current temporal GNN framework, that's a PyTorch geometric temporal, it only supports full batch training and also is constrained to snapshot-based methods, right? And this was, of course, some time ago when we did this research. Maybe now things changed, but at the time we realized there is a need for a general and efficient temporal GNN framework, and we developed the TGL, right? So the TGL consists of several building blocks. The first one is the node memory. So here, these building blocks actually are common across algorithms, right? So we want to identify what are the common building blocks across different graph neural networks and build a framework that will optimize each of these building blocks. And the optimized implementation will help all the GNN models, the temporal GNN models, to scale. So the first one is called node memory, essentially summarizes the past node states and updates the messages by using events, what's called events. The next one that we are considering is the attention aggregator. Essentially, is a method to aggregate the messages of your neighbors, what Da also showed earlier, actually based on attention. And this attention-based method is actually providing very good results in practice. And finally, we have the temporal neighbor sampler that decides how to sample in your neighborhood. Because now we have actually neighbors over the space domain, so we have some spatial neighbors, and we also have some temporal neighbors, right? So there are two dimensions of sampling that we need to consider. So, and there are different approaches that either sample past neighbors uniformly or sample the most recent neighbors. And essentially, these are the building blocks for the TGL library. So the contributions of the TGL work, which you can find actually published in VLDB, is essentially a very efficient data structure that allows you to develop parallel samplers, a multi-GPU training scheme. So this multi-GPU scheme is one of the first schemes that is provided for temporal graphs. And actually, it has a very smart way of using one process essentially to sample over time and the others to do the computation. It also uses a random chunk scheduling algorithm that essentially breaks a batch into chunks and allows you actually to use a larger batch size within the training. This helps you achieve better performance in practice. And also we introduced two large-scale temporal benchmarks that really help you showcase the value of essentially scaling these temporal graph neural networks. So I know I go a little bit fast over that, but you can read a lot of more information in our published paper. Just to give you some glimpse of the results, we have here we compare essentially the baseline results that are the implementations provided by the authors of these papers. And here we provide the TGL results, which is the implementations by the library, the TGL library. So what we see here actually is in two data sets that are actually small case data sets, because these approaches do not scale to the large data sets. So we see an average of 30x speed up, but we also see actually in this little graph, we see that the performance also improves. So here on the y-axis, we have the performance, on the x-axis, we have the training time per epoch. So what we see is that the baseline methods are slower and also less performant than in red one. In red, you can see here the TGL methods. This tells you really that the method, besides being more efficient, it also achieves better performance. we attribute that to a large extent to the random chunk scheduling algorithm that allows you to essentially give better performance during training. And we also have here some profiling of we also have some profiling here of how TGL works on really large scale datasets, which is essentially a very important topic because there has not been any method scaling to these datasets before this implementation of TGL. So yeah, so this was a wonderful work by our intern, Hongwan, and next, I move to another piece of work, again, actually done by one of our interns, and actually it was accepted in this tutorial, in this conference, about how we perform active learning with GNNs. And the question here that we are trying to answer is we are solving a semi-supervised learning problem on graphs, right? And we are trying to answer, can we select which nodes to annotate to improve the GNN learning performance? Essentially, this is the typical active learning setup, right? So you have some samples over your graph, right? So you have some observations and you want to predict the rest, right? But now I also tell you that you have a budget and you can sample more labels. So which labels should you ask to essentially annotate to get most important performance? So this is a very important task that can help you essentially improve using less training labels to learn a better model. And it is really actually important for, especially for the large scale graphs that we are discussing in industry. So, in our work, so the first thing you usually do in active learning type of scenarios is you are trying to sample the nodes or to select the nodes that your model is most uncertain about. So the nodes that have the highest prediction uncertainty should be selected as the nodes to be labeled. So this is natural if you think about it, right? So if there is a model that makes some predictions for the nodes that you are most uncertain, you would want this to be essentially labeled next. So this is the typical active learning setup. But we realized that this setup may not be very good for the graph setup. Why? Because selecting nodes in this way may select nodes that are clustered in one region of the graph, and we will end up under-exploring the whole graph. So the follow-up question we're asking is, how can we diversify these uncertain samples? So we know that these are the most uncertain nodes, so how can we find a way to diversify the sampling? And the algorithm we implemented is actually quite simple, but provides some reliable guarantees. So we first select the M most uncertain nodes, and then we propagate their input features. Then we cluster the propagated features in capital C clusters, and then we query the C nodes for their labels that are closest to the cluster centers. So what we are doing here is we are taking from the uncertain nodes the ones that are essentially more spread out, essentially, if you think about it in the graph structure. And this allows us to explore well the graph and also achieve the uncertainty goal. And our results are also have theoretical results that confirm the advantage of this diversification method for the uncertain samples. So yeah, you can find more in our paper that's available in archive and was published in the LOG conference, again led by one of our brilliant interns. And for the next I think like final part of the talk, I want first I want to show you some results of how does this method works in practice. So this algorithm is data efficient. What does this mean? So in these plots we show on the y-axis the test accuracy. On the x-axis, we see the sampling ratio. So essentially, so how do the algorithms perform as we sample more and more nodes, right? So what we see here is essentially all algorithms start based on some performance, right? And then we sample certain nodes essentially based on different active learning methods, right? How to sample. So what we see is that our method, comparing to the second best alternative, is 50% more data efficient in the sense that it achieves the same performance by using half of the labels. And like this is really important because you can imagine that this half of the labels as the graphs scale, and here we're talking about OGBN product, that's a relatively large graph around 1 million nodes. So as this data scales, right, so we will have more and more savings or on labeling costs. But again, I urge you to read more in the paper. So I want to take the final maybe 5 or 10 minutes to go over our last work, which was essentially how can we train efficient and effective language models and graph neural networks. So in this work, we are actually talking about a more realistic application, right? So first of all, you can think that in an e-commerce giant, like let's say like Amazon, right? You have buyers, right? You have sellers, you have products, right? You have reviews, right? And all of these things, you can see them in a multi-entity graph, right? So you can imagine the buyers interacting with the products interacting essentially are sold by sellers, and this will create a heterogeneous graph structure, right? Besides this heterogeneous graph structure on this rich graph, we also have rich features. So each of the nodes in the graph is associated with, for example, rich text features. So each product has a title, it has a description, right? It has images, and the same with the reviews, right? So the reviews have some kind of text, right? And the question really here is, how can we build a tool that will encompass and generate one representation that will account for everything, right? So the very first thing, simplest thing you can think, right, is apply a text encoder like a language model or a transformer to get an embedding of a high dimensional embedding of essentially the review text, right? And then you will be using this review text on a downstream task, and this will exploit the rich textual features in order to generate essentially a single embedding. So, of course, the next thing you can also imagine is how you can, use this graph data in probably using a relational GCN model, right? So this relational GCN model will take the graph data and will train a link prediction task, such this structure prediction encoder. Decoder means that we are applying a link prediction loss in order to find embeddings for every node in your graph. So we have essentially this multi-relational message that we also discussed earlier, right? In DAS presentation, right? And you also have this update function to find the update for the next layer. And essentially this will exploit the graph structure to generate multi-entity graph-aware representations. So here, in the previous slide, we see essentially a model that can capture the text, the rich text. And in this slide, we see a model essentially that can capture the rich graph structure. So how do we combine the two? Of course, maybe there is an obvious answer for in your mind, which is essentially, of course, putting essentially a transformer model that will, ingest the title of the products or the review content, will generate a vector, and then this will be fed into a GNN model. And this will be all trained with a link prediction loss end-to-end. But as you can read in our paper that is referenced below, this very obvious thing is not very easy to implement. Reason is that there are challenges related to efficiency. So here, essentially, we are talking about the classical two-hop neighborhood explosion problem. So you have one target node, you expand his two-hop neighborhood, and you find essentially hundreds of nodes, right? Let's say 400 nodes. It's a typical example. So then, practically in this composite model, you need to have 400 passes through a language model for a single target node, which means that you need to keep the gradients in the GPU memory that will quickly run out of memory if you are talking about a batch of relatively large size. So there is a lot of challenges related to efficiency. And also, how do we do that on a trillion edge graph? So to solve these challenges, we use a lot of the tools that Da presented earlier, also distributed DGL, but we also are making some innovations specifically targeted for this type of model. And finally, the other challenge relates to effectiveness. So how can we effectively train these models? So effectively training these models is not so simple as, stitching everything together and doing the back propagation, right? So what we notice is that we need to perform a stage-wise fine-tuning of those models in order to get benefit. So in the interest of time, I will skip the next 2 slides, and I will give you our solution simply with images, because I think it's easier to follow, and also we don't have so much time, I think. So our stage-wise fine-tuning framework for the effective training of language model GNNs consists of 3 steps. So the first stage relates with essentially how we do the graph-aware pre-fine-tuning of language models. So what we observe is that these language models are very well attuned to predicting language tasks, but they are not so well attuned to predict graph tasks. So what did we do? So we apply a supervision method to these language models in order to make them graph aware. And practically, we are trying to predict links in the heterogeneous graph that we discussed earlier, using the embeddings generated by the language models. And this will actually give our language models the graph aware component. So the next step we are actually doing here is to do warm starting of the GNN models. So after we get these well-trained language models and we stitch them together with a randomly initialized GNN model, we observe that we don't get the convergence we really like. So what we do is that for a few iterations, for a few epochs, we only backpropagate the loss from the link prediction objective to the GNN encoder. So in this way, we are warm starting the GNN encoder. And then this is like our second step, right? And our third stage, we are actually fine-tuning in an end-to-end fashion, right? We are fine-tuning in an end-to-end fashion the whole language model GNN architecture. So this is the whole pipeline that we use to effectively and efficiently train the language model GNNs. And we realize some value of this architecture in internal applications, but also in public benchmarks. So here in the next slide, I will show you how this method performs in public benchmarks. So first, let me pull everything together. So the stage-wise fine-tuning is effective across tasks. So table 1 has the node classification tasks, and table 2 has the link prediction tasks. So what we see with row 6 in table 1 and row 7 in table 2 is our 3 stages of graph-aware pre-fine-tuning of the language model GNN. So we see that with bold, we see the best performing method, and we see that in any case, these 3 stages always help achieving the best possible performance. So this architecture that we have built essentially has benefit in this type of tasks. So let's talk a little bit about the data that we use, our graphs. So we use the archive graph and the products graph that are the OGBN benchmark data that provided by the OGBN benchmark effort. So this data have actually, there is a graph structure there, but every node in this graph has a rich text. And also the Yelp data. So the Yelp data have also this kind of format. So there is a graph and there is a rich text for every node in the graph. So, and for example, if you compare, let's say row 4 with essentially row 6, that is essentially our 3 stages. So row 4 just does the end-to-end fine-tuning of everything without doing the 3 stages. And you can see that it really doesn't perform as well as essentially performing all these 3 stages. And actually the difference is even more prominent in link prediction tasks. The reason for that is that we observed that in link prediction, actually doing this essentially graph-aware pre-fine tuning of the BERT model is very, very essential for link prediction tasks. And this is this summary of these results. So before concluding this part, I wanted to say, like, we have a lot of ongoing research efforts, and we are encouraged to seek academic collaborations in order to solve these very difficult and challenging problems. Because the only way we can really move forward in this field is that if we all like work together and reuse the scientific advances that someone makes. So we really appreciate any contributions also in the DGL library. And we have developed two products, and now in the final half an hour or 25 minutes, Soji will talk to you about our most exciting like AWS offering that allows you to do graph neural networks in scale. Thank you.
Yeah, so hi, my name is Soji. I'm also an applied scientist at AWS, and I work with Vassilis and Dara on the graph machine learning team. And so, yeah, I hope you've been sort of enjoying the tutorial so far. This is the sort of third section where I will talk about how you can deploy GNNs for real-time applications. And I suspect, like, if you're interested in sort of like how models like that you may develop get sort of deployed to production to maximize business impact, then this section would be interesting for you. So to give you a rough idea of how the section will go, I think I'll start by talking about some of the real-time applications that we're interested in solving at AWS and Amazon, and talk about why GNNs are actually well suited for those kinds of problems. But they're also not without their challenges in terms of like stitching together sort of like different components to make these applications work, right? So I'll talk about some of the advantages that GNNs have, but then also about some of the challenges. And then like towards the end, I will sort of motivate why you need a highly available graph database to solve some of these problems, and then talk about EpchinML, which is a tool that we built on top of AWS's highly available graph database, which is called Amazon Epchin. So let's get right into it. I think we may not have a lot of time for questions at the end, so please feel free to put them in the Slack channel. I think it's like tutorial day 1B, and I'll be able to answer them afterwards. So, so getting right into it, like one important real-time application that we have is fraud detection, right? Like, and so fraud detection is an area where graph-based methods tend to outperform non-graph-based methods. And it's also an area where real-time predictions is impactful. So like, you may already know, right, that like a lot of businesses, online businesses, lose billions of dollars every year to fraud. Now, you can sort of imagine a scenario where you tackle this on a static graph, right? Like, so you take all the transactions that has occurred on your online business platform, like say, for example, over the past 2 weeks, and then you like train a model on this, like in a sort of maybe semi-supervised way, and then apply the model to generate predictions. But all this is going to tell you is sort of like the retroactive predictions, essentially for transactions or things that have already happened, like, then you can take action to prevent further losses. But having a real-time, like, or near real-time prediction is very powerful in these use cases, right? Because you may imagine a situation where someone adds a new payment method, like a new credit card, and you want to predict as soon as that event has occurred, does this change like what I believe about this person as to whether they're a sort of, benign or malicious actor, or like even as early as like when the user is registering for a new account and like putting in information about like, and you can collect information about like, some of the identification information, then you can, at that point start to like, detect things like collusion. And so you may want to sort of, like proactively limit the kinds of things that the user can do. So being able to get predictions right as soon as like events are recorded that change the topology of the graph is so very crucial to this application. And it's one of like the biggest drivers of like using graph machine learning and also GNNs in production. All right. Another example I'd like to give is one with sort of social network recommendations. So you can imagine a social network question answering site like Stack Overflow. So like there are a couple different internal and external AWS versions of this, where people that have questions about like, technical questions about the cloud and things like that can go and ask questions. And we have a number of experts, right, that know, that have sort of domain expertise that are able to sort of answer some of those questions, right? And in order to sort of, improve the overall user experience, you want like questions as soon as they're answered to be sort of routed to like one of the potential experts that can answer this. So you can kind of think of this as a link prediction problem, right? Like, so you can have different nodes in the graph, like users, like question askers, tags, and things like that, right? And then you want to predict, as soon as a new question comes in, like which of my experts can I route this to in order to get like the right answer for the question. And having this done in real time or near real time is also very important. Right. Another one that's like, also really impactful for like a large e-commerce firm like Amazon is product recommendations, right? Like, so you imagine a user sort of browsing through different pages, and as they go through from page to page, we want to be able to generate sort of like some of the best related products. So I hope this is sort of like, motivated for you some of the reasons why we need sort of this real-time applications and why they can be impactful. Now I'm going to talk about, GNNs a bit and like why, some of the advantages that they have for some of these applications. All right, so you guys may already be familiar with graph neural networks. Da sort of introduced them at the first section of this tutorial. And yeah, so like in a lot of the applications that we work on at Amazon, we see that GNNs provide sort of like sustained performance improvements over some of the sort of traditional like shallow graph representation learning methods, and sort of achieve state-of-the-art performance in many tasks. Like as you can like, so Vassilis introduced some of those tasks like where we are sort of mixing in language models and GNNs, right? And like particularly because GNNs can be sort of trained in a very scalable fashion, like sort of, so going back to what Da talked about in his slide, like with tools like this TGL, and they can sort of, be applied over dynamic graphs. They have these sort of natural advantages for some of these applications that we're talking about, right? So like one particular benefit to really call out is that unlike sort of shallow embedding methods, the GNNs and the downstream models can be trained end to end, right? Like, so the whole thing is fully differentiable, right? And so this is very convenient for sort of like production applications, right? Because it means you don't have to like have a sequence of steps for training and retraining. You can just have a single sort of state you can think of that or stage that is responsible for the end-to-end training. And like, sort of time back to like what Vassilis was talking about with some of the active learning stuff, like as soon as labels are available, you can automatically retrigger retraining, like either based on when they're available or based on like a schedule, right? So so for shallow embedding methods, you need to have like multiple separate workflows, but with GNNs, you can essentially have a single one that's like sort of directly supervised. And this also means that like on the same graph, you can train sort of multiple GNN methods and have them sort of share like infrastructure, right? Like, so because, you could have different properties supervising different GNN models, and then you don't have to make a whole new pipeline for that. So you could have a centralized graph and then multiple different models on top of that, which is something that like is very convenient. And then another sort of benefit is the sort of inductiveness of GNNs, right? So in order to sort of make a prediction or like compute the graph representation for a particular node, as you may know, you just need to sort of get out the computational subgraph that is needed for that node's computation. So you get the ego network, and the same model sort of can apply to that subgraph, right? Like regardless of what particular node it is. So for dynamic graphs, this is super important, right? So again, sort of contrasting with like maybe some traditional methods, right, where you would pre-train the node embeddings, but then when a new thing comes in, then you wouldn't be able to like, have a representation for that. Even though like with pre-trained embeddings, simply looking up pre-trained node embeddings takes very little time, but just the inflexibility of dealing with new stuff makes that problematic for the shallow embeddings. Right. And so far I've talked about just some of the benefits. Now let's talk about some of the challenges. So these challenges don't mean that like GNNs aren't well suited for like real-time applications and like deploying on the cloud. It just means that there are a number of problems that we would need to solve in order to have a sort of end-to-end workflow that works very well. So like I listed a few here, like, initially the problem of sort of training multiple models, right? Like, so doing search over a large hyperparameter space and also over a large model architecture space. And so I'll talk about how, some of the tools like this DGL and like, like some of the AWS services that we provide, like enable us tackle some of this. And then there's, challenges that you need to solve with regards to the actual real-time prediction, right? Like, so, being able to handle streaming in data that like sort of dynamically updates the graph, right? And so this is one big area where we rely on sort of like, AWS's expertise for building these high available services in order to sort of, leverage some of the stuff that we already have in-house. And then sort of extracting out the computational subgraph and neighbor sampling. This go hand in hand. Like would need to do this in real time as well for these applications. And then also, doing like for link prediction, you have to do like apply the decoder, which typically sort of is essentially comparing and embedding with like a bunch of embeddings across the whole graph, and so speeding that up. And then also automating model retraining. So I'll go through some of this in like a bit of detail and just like really quickly talk about the problem and like how we sort of address that. So like one problem is sort of, how do you maximize the training budget to ensure that we get the best model for that budget? And so so the sort of typical way to sort of think about this is to do sort of, you have your configuration of hyperparameters and you do hyperparameter exploration, and then you try and figure this out. But then if you have a training budget, you want to be sure you're focusing on the right set of hyperparameters, right? And so what we've done is we trained a bunch of ran a bunch of experiments, sort of training multiple GNN models on multiple different data sets. And then we're able to bin hyperparameters and sort of model configuration into different tiers, right? Like, and so based on the size of the budget, so like if we only have, for example, 10 jobs to run, then we're only going to vary hyperparameters that are within a certain tier. And so we have this for like different kinds of tasks, like load classification tiers are different from link prediction tiers. And then, so when we select the tiers that we're going to vary, then we use Bayesian hyperparameter optimization to balance the trade-offs while searching over the hyperparameter space. And like, so AWS provides like a nice tool within Amazon SageMaker that like can sort of do this for you. And like one, as I mentioned previously, big problem to solve is how you maintain the dynamic graph for predictions. Again, you can imagine sort of just information streaming through from the source, and the traditional deep graph learning frameworks are not suited to like updating graphs this rapidly, or even storing like, free-form data like heterogeneous property types for nodes and edges within the graph. And so what we do is we essentially rely on Amazon Neptune, which is the cloud graph database that AWS provides. And that sort of acts as the sort of online data store for the graph, right? And we can access, subgraphs and run queries on this with like millisecond query response times. And so this is like, if you're familiar with the language, more of like a OLTP graph framework, which allows us to like really quickly query subgraphs and then transform those really efficiently and then use it for the online prediction. Right. And so once we are able to sort of extract the, once we're able to identify that like we need to use a graph database, another problem that comes up is that the query languages that are commonly used, like the standard GraphDB query languages, are not really designed for extracting out computational subgraph for inference. They're more designed for like answering like very simple graph queries. And like, but so what we've done is we extended some of this, we extended the graph database framework and built in custom subgraph extraction ops in the graph database. So we were able to do things like, you know, automatically batching together multiple ego networks for different target nodes. And then we can sort of fuse them and form like a bigger computational subgraph that we can then sort of like, you know, sort of transmit to the model inference pipeline in order to sort of do the model prediction. In order to also save some, like shave off some time, we perform the neighbor sampling within the graph database as well. So this allows us to like, you know, save on, you know, the time for doing neighbor sampling at inference, like on the model computation side, but also reduces the size of payload that we have to communicate across to the model, which means that like model, which means that like that communication also happens faster, right? And then the last sort of like challenge I want to focus on is, you know, you can think for specifically things like link prediction problems, where you want to compute scores for a particular target node to see which other nodes in the graph are going to be most likely to form a link with this. So this target node might be a new node that's coming in, but the set of response nodes or your candidate nodes are going to be, you know, on the sort of like existing static graph, right? And so like applying the link prediction decoder across this whole thing is very time consuming. And so we really sort of came up with two different key things to tackle this. One is sort of relying on like very highly optimized vector search libraries. So we use the open source library FICE, which is like developed and open source by Facebook. And so we will build a FICE index over all the node embeddings. And then when it's prediction time, when we compute the embedding for the current target node, we just essentially use the FICE index to do the retrieval, right? But that's not the full story, right? Because on the index, right, the indices aren't designed for, you know, generic link prediction decoder tasks, right? So if you imagine the decoders for GNNs or for knowledge graph embedding modules, like they're not essentially just you know, Euclidean distance, right? And so what we've done is when we save the node embeddings, we actually will do some pre-computation to merge, for example, like the relation embeddings with the node embeddings before building the index. So we can like sort of reliably convert or approximate the link prediction decoder scoring metric to something that can be done with like a FICE index. Right. So all of these different challenges that I talked about and the different solutions that we have developed are what we sort of put together into this sort of scalable tool for easily building graph neural networks on top of a database, on top of a graph database that we call sort of Amazon NextGNML. So the model building part of Amazon NextGNML is powered by, you know, DGL and this DGL, like that Da introduced earlier, which allows us to scale to very large data sets, like including, you know, sort of billions of nodes, right? And as Vassilis mentioned, one of the sort of main objectives of our team, one of our tenets is sort of expanding the number of people that are able to use machine learning on graphs, right? And like expanding number of businesses that are able to deploy solutions using GNNs. And so Amazon NeptuneML, in order to use it, you don't have to necessarily be a graph expert. You can just be an application developer that's actually just more familiar with the sort of nuances of your business problem and your graph data model. And then, with a few clicks, you can, train a GNN model where we handle a lot of the undifferentiated heavy lifting behind the scenes. And the encoders that we use in NeptuneML are sort of GNNs for, some of the reasons I mentioned before in terms of increased performance over competing models, as well as being able to deploy them for real-time impact, like for dynamic graphs essentially. And so the way NeptuneML works is that it makes it easy for you to do GNN experiments from within, from just having access to the graph database, right? So there's a couple of different steps, right? Where first you're exporting the graph data, and then we use DGL and DistDGL to train the GNN model. We sort of manage all of the hyperparameter search as well, and it's also sort of we're able to sort of decide what models can be applicable to what settings, right? But this can be overridden. For example, we have a custom model support where you can define your own GNN model in DGL, but then sort of wrap it within NeptuneML architecture. And then once the training is complete, then it's again just one simple API to deploy this. And then and once it's deployed, then just in the remaining few minutes, gonna show a demo of how you can really use that from within the graph database. Right, like I said, so the final step, once you have your model deployed of working within NeptuneML, is to use graph queries to infer based on the ML models. And so what NeptuneML allows you to do is you can execute graph queries that sort of within them contain ML predictions. So here we have an example of a graph query in Gremlin. So Gremlin is an open source graph query language for Apache Tinkerpop. So it's very common language that's used for label property graph models, right? And so here we're just saying, get the vertex Bob and the edges for the movies is liked, and then give me their titles, right? And so you can see this just queries directly the database, and you get something like A Bug's Life and Monsters, Inc. But then what NeptuneML, you can just add this with decorators to say with this endpoint and with NeptuneML prediction. And so what you get now is this virtual edge that doesn't exist, but you can sort of write a query as though this edge was, and just sort of getting it out actually from the prediction. So sort of showing some real life examples of that. You can see this is the actual sort of notebook environment and the Gremlin annotator. So it's a similar query to the one I showed in the slides, right? Where you have user one, and then you want to get the outgoing rated edges with the prediction. And then you can see the most likely predicted movie that this user one is going to rate is The Devil's Own, which came out in 1997. And then you can also do reverse predictions here, where you have for this particular movie, Toy Story, give me the users that are most likely to have rated it, and then give me 3 of them. So you can so vary things like the limits or the top K, and you can also get things like the score, right? So here's another example, so showing the power of being able to combine these predictions with the graph traversal, right? You can do visualization on top of just the prediction, right? So you get a prediction, and then you can intermix predicted things and things that are in the actual database, right? And so here is another example for a classification task, right? Where, for this particular vertex, you're trying to predict the is fraud property and also the score, so the predicted probability that is assigned by the model, like the GNN model. And then you can get that this is predicted as non-fraudulent, and this is the score, right? And this is also a very powerful, another example that's very powerful, right? Because this is actually a mutation query and a prediction query at the same time, right? Like, so you see we are adding this transaction, sorry, let me just go back, as ID 99999, and then our prediction, like, so is on the thing that we just added, right? And we just want to predict the is fraud property. So you can imagine like the end client making a mutation query, and then as soon as that's added, sort of requesting for inference. And then there's a couple of different things that you can toggle around, whether the prediction should be deterministic in terms of like how the neighbor sampling is done versus like random and things like that. So to quickly summarize, right, like GNNs are state of the art in many applications that we solve at Amazon and are suited for real-time predictions. But in order to unlock them, we need to sort of, coordinate tightly with a highly available graph database for real-time applications. And there are these multiple challenges that arise. And like the goal of NeptuneML is to make it so that you don't have to deal with these challenges as like a user. We sort of handle all of that and sort of build on a lot of the building blocks in terms of like this DGL, DGL, DGLKE, but like sort of make them, friendly for like enterprise and also like independent users. And so that brings me to the end. Just gonna show a couple of quick resources for you to reference, right? Like, so you can learn more about NeptuneML. You can just Google NeptuneML, and then you can also learn more about DGL. And finally, please fill out the feedback form at the end of this, I think, in terms of like, rating the like sub tutorials for the log organizers. Thank you very much for listening.